local galaxy, which is just an island, a gravitational island in the universe. One among hundreds and hundreds of billions, if not trillions, of other galaxies, and a bit player, really, in the larger structure of the universe. And I thought that was pretty awe-inspiring, because we didn't know this until I'm looking at it here, less than 100 years ago. So 1923 is when Edwin Hubble found a Cepheid variable, and my audio got screwed up on that episode, but maybe it's still worth checking out the episode on Edwin Hubble I did a few back. And I tried to explain in that one the importance of Hubble's discovery. So we're going to start with the Andromeda Nebula and talk about, from there, branch out to the rest of the galaxies in our local group. And along the way, I'll be using this study guide created by David Butler, who has an entire channel dedicated to teaching people the actual science of astronomy in a very, I'd say a very ASMR-esque tone and style. So I would highly recommend you go check it out. Hopefully, with any luck, my future self will remember to put the link in the description. And I'll try to use this book along the way. Visible to the naked eye and studied by Persian astronomers around 900 AD, the Andromeda Nebula was thought to be a part of the Milky Way, which makes you wonder what it is that we used to think our Milky Way was. So I think it's pretty interesting that it's like analogous to being in a cave, and then maybe, perhaps, other than your echo, you have no idea how big the cave is or what's right in front of you, and for millions of years, if not, at least hundreds of thousands of years, I'm sure we were, as a species, we were looking into the sky and we were seeing the infinite, but we had no context in which to put the stars in. And literally a blink of an eye ago, yesterday, in cosmological, a minute ago in cosmological timescales, we discovered that we're in this galaxy that's 100,000, that takes light 100,000 years to cross, but that's nothing compared to the actual scale of the universe that we're aware of now. And I don't know, I guess I should look into how far away we thought the most distant object prior to that actually was. I think I remember reading something like 200,000 light years I think that 1,000,000 light years was completely out of the question. So, to me, that's just fascinating that our perspective on the universe has changed so drastically just such a short time ago. It's amazing. But let's move on. Hubble was the guy who initiated the paradigm shift in cosmology, and he found this Cepheid variable. In what he called a nebula at that time. This star altered the course of modern astronomy. The star is called V1. So here's a shot of Edwin Hubble's image of Andromeda, which he made on a 4x5-inch glass plate. It's from October 6th, 1923. He originally identified 3 stars and marked each of them with a N for nova. He thought they were exploding stars, but later he realized that the nova at the top right, the one that says VAR exclamation point, was actually a Cepheid variable. And that's what I'm going to look up real quick in this book, my encyclopedia. So he, once he realized that, he crossed it out. And he crossed out the N. So the reason he added the exclamation point was because he knew that this variable would allow him to calculate the distance. And of course, that was one of the leading mysteries in cosmology back then. I mean, still really is. Still really is, like exactly how far away certain objects are. And it blows my mind that we're able to verify with evidence and in a reproducible fashion just how far away Cepheid variables are based on their characteristic periods. And so we know that, let me look it up real quick. So this period of the V1 Cepheid variable star had a period of 31.4 days. And before V1, distances to stars were measured in thousands of light years. But after V1, the universe got much, much bigger. Using his using what I'm about to show you, he realized that the universe, or V1, was over 2.5 million light years away. God, that's so big. So that's amazing that he was measuring it in just thousands or tens of thousands of years, light years. And then all of a sudden the science, the facts that he was so used to, so familiar with working with, and so often gave him just a distance of a couple thousands of light years. It popped out the result of 2.5 million light years. So to me that's so it's like a juxtaposition of the mundane nature of science with the occasional flashes of insight and awe and radical change in perspective that you're given if you stick it out, which took him years to do, by the way. So if it wasn't for his persistence, we would have never known that, or at least it would have taken someone else a lot longer, I'm sure. So here I'm going to show you a graph. Studying the light curve for V1, Hubble determined its luminosity. I'm going to try to look it up while I can here. Measuring its apparent brightness here on the Earth, he calculated the distance. So remember that our galaxy is only about 100,000 years wide. So, in that perspective, V1 was definitely too far away to be a part of our galaxy. Classifications, series, Cepheid variables. Okay. Page 42. Getting close. Look at that. I just think that. Hopefully you guys can see that. That picture is so amazing. I think that is so much more creative than a lot of the CGI that Discovery Channel, the universe and shows like that use nowadays. They're getting better, but to me in particular, I think it's, I don't know, those shows they used to really impress me, but they seem to be just a lot more, what's the word? I don't know, just kind of phoned in and watered down. It's not really as in-depth scientifically as someone like David Butler gets. Okay. So, Cepheid variables here. See if I can make sense of what I'm looking at. So, here I found a little excerpt about Miss Henrietta Leavitt. In 1908, she was studying the Magellanic Clouds. At that time, the distances of these clouds were unknown. Although we now know that they are neighboring galaxies, 50 kiloparsecs distant, but they were clearly sufficiently remote for all their stars to be considered to be at the same distance. She noticed that the brighter Cepheids had correspondingly longer periods, and because of their equal distance, this showed the existence of a direct link with period and luminosity. So, however, the distance of at least one Cepheid was required to determine the absolute relation for the group. None of them were sufficiently close to show trigonometrical parallaxes, but studies of star clusters in the early 1960s established that the relation reproduced in figure 2.29, which is here it is right here. So I'll try to make this somewhat intelligible. The relationship between, on the y-axis, the vertical axis, was the absolute visual magnitude, and the x or horizontal axis was period in days. So the relationship between these two for classical Cepheids is W Virginis and RR Lyrae stars is what this is. So when you measure the period, it allows its absolute magnitude to be derived, and the measurement of its apparent magnitude then yields the distance of the Cepheid. Wow, that's really, really cool. So, there's a tight link between the period, how many days, and it goes all the way from, looks like just under 3 days to over close to 100 days for classical Cepheids. And the longer the period, the dimmer the magnitude, the absolute magnitude is. So cool. So I guess it would be analogous, like you do see on those shows, that if a car's headlight is, if we thought of it as, well, maybe a lighthouse would be obviously a better analogy. So if we knew the period of the lighthouse, and we knew that corresponded to, say there were standards set in practice, and maybe there are, that would be really interesting if there are. There's a couple of you out there who are talking about maritime nations and principalities, I guess. I might know the answer to that, but if we knew that the lighthouse rotated, once every 2 minutes, and that was its period, and every lighthouse that has that period is set to a certain standard luminosity, then regardless of how far away you are, you might be able to determine the distance of it to an approximate distance. Trying to work that out, how that would work. And I suppose it would just be some equation, some function of how much dimmer the light is, how much dimmer it appears to you if you were a ship out at sea than what you know its standard absolute luminosity to be. So if it's just a little bit dimmer, you know that you're much closer to the lighthouse and shore than you might otherwise think. And if it's very, very, very dim, then you have a good idea, because the period won't be altered in any way, any significant way, depending on your distance. That period is still consistent, I guess. So that's really cool. That's the one constant that is throughout that phenomenon. So going back to V1 now, that our little light curve showed. V1 was definitely too far away to be a part of it. To be a part of our 100,000 light year galaxy. And this also meant that because it was a part of a nebula, all the other stars in that nebula had to have been that same distance as well. So this made V1 the most important, one of the most important stars in the history of cosmology. I think it's, I don't know, I just can't get enough of that. So Andromeda is a beautiful barred spiral galaxy with two spiral arms that glow with a massive number of new stars. This is a lot like our Milky Way, but it's over twice the width of our galaxy and contains, instead of only about 100 billion, it contains over 1 trillion stars. God, so many. So it's got about 10 times as many stars as our Milky Way does. And light from this magnificent galaxy left its stars over 2.5 million years ago. Oh, man. So when the light that entered Hubble's telescope in 1923 finally made it there, or sorry, when it left its original galaxy or star, humans weren't even evolved yet. Our ancestors were still, I guess, just barely becoming familiar with fires and flintstones. While the light traveled towards Earth, we came into being. Our consciousness in our brains evolved significantly. We changed physiologically. We created and lost great civilizations. And we built telescopes that caught the light when it finally reached our planet. Now Andromeda has I assume all galaxies, has a central black hole. Here we see the 100 million solar mass black hole at the center of Andromeda. Its core, really. This is the sharpest visible light image ever made of the nucleus of an entire external galaxy. And you can see here there's a blue glow around the center of what happens to be a double nucleus. And in fact, using the Hubble Space Telescope, astronomers were able to identify the source of the blue light surrounding the supermassive black hole. New spectroscopic observations revealed that the blue light consists of more than 400 stars. Stars are tightly packed in a disk that is only 1 light year across. Put then to perspective, our nearest star to us, to our star, our sun, is 4 light years away. So it's gotta be 0 dark skies if you're a planet on those stars, which I highly doubt. It's not, it wasn't, yeah, I'm sure it's too chaotic to have developed life on those, but that'd be interesting if it did, I suppose. So the disk is nested inside an elliptical ring of older, cooler, redder stars. When the stars are at the farthest point in their orbit, they move slower, so they give the illusion of a second nucleus. Astronomers are trying to understand how apparently young stars were formed so deep inside the black hole's gravitational grip, and how they survive in such an extreme environment. The fact that young stars are so closely bound to the central black hole in our Milky Way, it suggests that it actually might be a common phenomenon in spiral galaxies. So moving on to the local group now. There's a total of 54 galaxies in our local group. Andromeda is the largest. The Milky Way is the second, and Triangulum is the third. All the rest are what we call dwarf galaxies. So most of these are orbiting one of either us or the other 2 large galaxies. Ourselves, we have 16 satellite dwarf galaxies. Andromeda has 25, and the Triangulum might have 1. The other members of the group aren't gravitationally orbiting these larger galaxies.